Hi, and welcome to Lecture 6 of our Maps, Images and Structure class. And today we're going to do something new. We're going to start thinking about real maps and applying what you've learned up to this point to interpreting those. So, there are differences between the problem maps you've been working with and real maps. And some of the differences are outlined here. So, for one thing, we see that the thicknesses of the units actually vary across the map. Like you can see this example, these are the problem and the real map for a part of Scotland, and you can see like this grey unit here is changing its thickness much more so than you see in the problem map. And that also means actually that the dips don't always vary in a systematic fashion in the way that you've been looking at, and also that faults are not simple reverse or normal or strike-slip fault. They often have both dip and strike-slip components to them. So one of the other things which is different between the problem maps and the real maps is, of course, that real maps are not perfect. And that means that there are features on the maps, on real maps, that haven't really been identified, or they may not be located ideally. And that's particularly true in regions where the outcrop is poor and people aren't able to make good observations, and they have to just do the best they can. And what this means is that sometimes features have been simplified. This is an example here actually where they show onshore and offshore geology. And of course offshore we don't have great access, so these are quite simplified. They're essentially good guesses, and that's all we have to work with. So the other feature is that things that are marked on the map don't go on forever. Everything you've dealt with up to this point involves units that essentially extrapolate uniformly to the edge of the map, but that's not always true in real maps. For example, faults or dikes or folds, they don't extend forever in the real world, and they don't extend forever on maps. This is an example of some short pink-coloured dikes, igneous dikes here. They may really be this short, or they may just simply be going under the grass and nobody knows where they go, so they only mark the bit that they are sure of. In the same way, faults will peter out, and even stratigraphic units may pinch out, so they don't go on forever. And that's something that's a bit different, and you have to think about that. One of the other aspects that's more complicated is the fact that a lot of real maps cover quite large areas. So here, for example, is an example with the Isle of Anglesey and North Wales, parts of northwest England here as well. So this is a pretty big area. Most of the maps you've been working with just cover a few kilometres. This one is maybe over 100, probably over 100 kilometres here. So potentially, therefore, that means that they are more complicated because they have lots of different features on them, and there are different things that are interacting with one another that make it more difficult to interpret. Of course, one thing that is an advantage is that for any particular area, this means that you might be looking at an area where people have been doing research, not just making a map. And as a result of that, there may be more interesting information on the rocks that you're interpreting in the literature, and you can go look that up. That will help you to interpret the map patterns that you have in a regional context. So there's more to learn beyond the map itself. In the problem map, it's just the map tells you everything, there is nothing else. But in real maps, of course, that's not true. People have been there and made observations and measurements which may be relevant. So let's talk a little bit about stratigraphy and the hierarchy of stratigraphy, which is important when you come to look at complicated real maps. So, stratigraphic units, what the hell are stratigraphic units? A stratigraphic unit is essentially an assembly of beds that have been lumped together into groups, and that means They're usually sedimentary rocks, but not always. You can have lavas, either by themselves or within a sedimentary section. Metamorphic rocks may not be fully homogenized, and therefore you can often see the layering in those. And essentially, what we're looking at is packages of sedimentary beds, obviously with the older one on the bottom and the younger one on the top. In addition to bedded units, we also get so-called non-stratigraphic units. So these are rocks which are not forming in layered sequences, and this is an example of one that you'll see when you go to northwest Scotland. So these are often intrusive igneous rocks or high-grade metamorphic rocks that have lost their bedding from their original protoliths, and sometimes they're highly deformed or destroyed by tectonic activity, highly tectonized rocks. So this example here, you can see pink granites and dark dikes which have been bent and folded. The whole thing is not evenly or regularly layered, so we can't really treat that as a bedded unit. So, however, for the rocks which do form nice bedded units, we can break this down into a hierarchy of observations, and going from the smallest end, which is just a bed, through to a member, a formation, a group, and a supergroup. And the formation is really the heart of the matter, because that's essentially the smallest mappable unit. When you go out into the mountains to make a geological map, you will see beds and you'll lump them together into distinctive packages, and if you can distinguish one package from the next, then you can call those two different formations. They have to be recognizable, and they have to be on a big enough scale to be mappable. A lot of maps are made at the 1 to 50,000 scale, and essentially if your formation is too small to mark on a map of that size, then it really is not a formation. So formations, they can be nice and boring. They may just be one single rock type, one type of lithology, or they can form a variety of distinctive rock types together. So for example, the one on the left here with green coloured shales and blue limestone here and more shale at the bottom, you could divide this up into three different formations: a shale A, limestone B, and shale C. If it's thinner bedded, you can still group these into distinctive packages. X, for example, would be mudstones and limestones, and so is Z on top here, but Y is a distinctive different formation because it has interbedded sand, which is shown as this pale orange colour here. So that would be distinctive there. You could map that as being a different formation that's different from X or Z. So within formations there may be special distinctive parts of the sequence that you can pick out as being a smaller unique division. We call these members, and essentially they just have to be recognizable, and they may be traceable across a map. They may not be everywhere, and sometimes people give them names, sometimes they don't. So this is an example of one here. We've got 3 units here, and a limestone A, the dominantly sandstone formation B, and then the shaly formation C on top. As you can see that within B there is this part here where we have shales and sands interbedded here. It's still part of this overall package, which means that it's part of formation B, but because it's unique, it can be mapped or defined as something special, like a member 1 in this particular case. Something unique, but on a smaller scale than a formation. And right down the smallest stratigraphic unit are beds. Sometimes these are distinctive as well. So for example, like here within the limestone formation B, here we have a bed of shale which is unique. That could be defined just as give it a special name like bed 1. You could call something like that member 1 as well. Usually members have more than one bed, but it wouldn't be the worst thing that ever happened, but they may be differently defined like that. Yeah, so it's the smallest division of the stratigraphic architecture. Yeah, and almost always beds are too small to go onto a map. You usually don't find special beds on geological maps. Right, and at the top end of things we have groups and supergroups. So groups are essentially packages of formations that have things in common with them. So essentially a series of rock types that have a common type of formation, and they may be lumped together as groups. So over here, for example, these limestone formations, dominantly limestone formations, may be lumped together as a single group, which is distinct from, say, the shale formation above of there. And of course, likewise, you can lump groups into supergroups as well. So typically you wouldn't have an unconformity within a group. This represents a big break in sedimentation, and groups would be more consistent, coherent sequences, even though they may change between formations within a group. So for example, here we have some examples of this. So we have a sequence here of limestones and sandstones and shales, and what you can see here is two different ways of thinking about these. So on the left here, this is one sort of breakdown here where they have a formation here for the limestone at the bottom, and then all of these sandstones with interbedded limestones and shales can be considered a single formation dominated by sandstones, but with, in this case, a special limestone shaly member in the middle. And then going up we would have a limestone formation here, and then back into a new formation right at the top of limestone and shales, with a member here that is characterized by a higher proportion of shale. On the other hand, on the right, this is a different but equally valid way of breaking up the stratigraphy, where essentially they have the limestone formation at the bottom there, but you see the member, the limestone shale unit that was considered a member over here is defined as its own special formation over here, and the coarser grained sandstone here is defined as a bed within a sandy formation there. So yeah, and you could see, yeah, and then finally at the top here we have essentially a limestone dominated formation here with a more shaly member at the top, in the way that this one was considered essentially a different formation over here, but you could lump them all together and just say that this is a member within this formation. So it's a bit arbitrary. You just have to make something that makes some sense. In general, you tend to follow what people have done beforehand unless there's a good reason to change that. So there are different ways of dividing up stratigraphy depending on what you're trying to do with the rock. So this is an example map. So you might make your geological map, say, to emphasize the rocks above the unconformity. Maybe you're doing a project that is looking at these younger sequences that are sitting above a deformed set of rocks here, so you don't care too much about those. You can just lump them all together. You're giving all your attention to the younger sequences. And of course the opposite might be true. Maybe you don't care about the young stuff, but you're really working on the folded material underneath here, in which case you leave all the detail under the unconformity and you simplify everything above just to say that it's younger than the unconformity. Also, the scale of observation may be important. So on a bigger map you might want to simplify more. On a bigger map it's likely to have maybe dozens of formations, which gets a bit overwhelming to the eye, so you might want to simplify that, break things down a little bit. And then of course conversely, if you're on a very small scale map, you might want to put in a bit of extra detail. If I asked you to make a map that was only half a mile square, then probably I'd want you to mark in all the formations, and not only just the formations but the members and the beds as well, so more detail when you have that opportunity. Just purely depends on what you're trying to get done and what you're trying to achieve, what you're trying to show, and the scale of the observation. So an example of this comes from northwest Scotland that you'll see in the field this coming September. So here we have a sequence with basement gneisses at the bottom, and then a series of sandstones shown in red here, followed by quartzites, the so-called pipe rock, which is a type of quartzite, and then sandstones here, the Sortarella grip. The fucoid is more of a limestone bed, and the Durness limestone right at the top of that. So we could simplify that if we so chose, depending on what we're interested in. So, for example, you might want to lump together the Applecross and the Diabeg, because these are both part of a so-called Torridonian group. They are unconformably separated from the Lewisian below and from these Paleozoic rocks overlying. Those could be mapped as one unit if you wanted to do that. Likewise, you could lump the quartzites together and consider those. The pipe rock and the basal quartzite could be considered. They are distinctive, but maybe that's not important to you for a particular purpose. You could lump them together. You can't, however, lump together quartzite above with the quartzites below, because they don't touch each other, so you can't lump them together like that. That would not be allowed. You could, however, decide to lump all the Paleozoic rocks together as a single group like that, and would be quite simplified. So simplifying geological maps is something you're going to need to do in your exercises going forward. And there are some simple rules to follow with this. First of all, we want to put together group together rocks that are similar to one another, and particularly fine-grained, small scale features like beds or members. We don't care about that on the regional scale. The important thing, however, is we want to be able to pick out and demonstrate the important structures, and as a result, we do want to be able to break down the stratigraphy enough to be able to resolve those. If you colour everything the same colour, you can't see any detail. We do want to be able to show some of the smaller structure as well, where possible. And again, that will help you decide how to break things down and simplify them. Let me show you an example from Northern England, from Penrith. So here we have Carboniferous rocks in the west, we have Permo-Triassic in the middle, and more Carboniferous on the right there. And like every real geological map, you will have a legend here showing the different formations, and as you can see, there's quite a lot of them, which is more than we need to get a general understanding of the evolution of this particular area. So we can try and break this down into an older sequences of limestones overlain by coal measures and the millstone grit sequences, and then sandstones and shales, the younger sandstones and shales that sit above that. So let's try this over here now. We are going to group together some of these rocks. These are the oldest rocks on the map. These are the Paleozoic, the Ordovician and Silurian that lie under all that, and potentially we could lump all of these together. The next youngest package is this Carboniferous sequences, limestones on the bottom and shales. You might think about lumping all that together. That might be too much, and that you're going to lose some of the detail there. If you map all of the Carboniferous together, and then we have the limestones below, and then the millstone grit above, and then finally the coal measures. So maybe that would be a smarter way of doing it, to show the three together separately in order to bring out some of the detail. So you have simplified from, say, like a dozen formations down into 3 packages in order to show the regional structure, and all of those lie on top of the lower Paleozoic. On top of those, we have Permian and Triassic sandstones and shales, and they represent a unique sequence. They are younger and separated by unconformity from the Carboniferous that underlies them. So again, those ought to be forming their own unique package, maybe even two packages. So this is the sort of simplifying that you could do. You can look at the Ordovician and the Silurian, the early Paleozoic, and you could map all those, put all those together. You could put your Carboniferous limestones as a separate group, and then potentially lumping together the Millstone Grit and the coal measures together. You might want to separate them, or you could put them together, depending on quite what you're trying to show. The overlying sediments actually are separated in time by one another, so although they appear to be one continuous package, it may be smart to try and break those out, the Triassic and the Permian, differently. And then when you apply that type of simplified scheme to the map, you end up with something that looks like that. So it's a lot simpler than what you saw on the real geological map, but it allows you to get an overall understanding of the geological evolution of the area. The lower Paleozoic in the purple here, over there, the overlying Carboniferous limestones in blue, the Millstone Grit and coal measures in grey, and then finally the overlying Permian and then Triassic. So let's see what we see here on this simplified map. We've simplified it, but not excessively, so that we can still see geologically important surfaces, such as this unconformity that separates the Permian and the Millstone Grit and coal measures here on the bottom of the Permian. We can also see a fault that's cutting through here, so this is important to distinguish between the Triassic and the Carboniferous limestones, and here the Triassic and the early Paleozoic. Down here, certainly getting the big faults on is important. Sometimes really big faults have names. This one's called the Pennine Fault, for example, that separates the Triassic over here from the Carboniferous limestones to the east, and we must make sure to get that on our map, like in this particular example here. And then once you've established the really big faults, you can put on some of the other faults to give a little bit of complexity, to show that you understand the main structures that define the outcrops. So not every little fault is going to go on, but you could put on some of the others once you've got your big faults down. And likewise on the west side of the map, here we define the larger faults here shown in red, and once we've got those down, you can add the smaller structures. So the best way to go about simplifying a map is to break it up into quadrants. So essentially we have to try and maintain the proportions. If you just hand draw a simplified map without using a grid, you're going to probably end up with something that looks pretty awful and unrealistic. So the idea is to put a grid down on top of your real map, and then you can use your simplifying scheme to draw in a series of little patches here that relate to one another, so that we keep the overall proportion of the main map, while at the same time simplifying the stratigraphy so that we can interpret it more easily. And then you would work your way, in this case from west to east across the map, until you'd completed a relatively simplified version of the geological map you're trying to interpret. So, good rule of thumb, what should you do first? Well, obviously the big and important stuff should go down first. If there's a giant fold or a big fault or a thick sequence of sediment, you should put those in, and then you can add in detail as you go along later. But get the important things down first. How much detail you add in is sort of up to you. You can't copy everything from the map. There's no point, otherwise you're not simplifying anything. But if you don't transfer enough detail, then the map is also not so interesting. A good rule of thumb I find is to draw things in from the youngest to the oldest, because then of course the young things tend to cross-cut the old stuff, and it's easier to draw it if you start with the young material on the top. So let's think a little bit about interpreting real maps. They're not, again, quite the same as the things that you've been looking at up to this point. Structure contours, well, you can draw structure contours on real geological maps, but in general people don't bother. You certainly don't need to do it. Instead, if you want to understand what the overall structure is, we don't have to draw structure contours, but we can use the strike and dip measurements which are shown on the geological map as a guide to this. So on British maps you often find strike and dip symbols of the type you've been practicing, but particularly on older ones you often see this arrow shape which is showing you the dip and dip direction, and then also the number here tells you the amount of dip. The strike of course would be perpendicular to that, so you have to be ready for both types of information. You might get the strike and dip symbol that we've been using, but arrows are pretty common. In general, we often only use structure contours to draw geological cross sections when we don't have that sort of information, when of course the topography allows that to happen. So by now you should have had a little bit of a feeling for what sort of outcrop patterns are most interesting and useful, and you can see these on the map as a first glance to try and help yourself to interpret the geology. So for example, if the stratigraphy is following the contours of the topography, we know that it's pretty horizontal. If they cut straight across of it, we know that the stratigraphy is vertical. When you find these T intersections between older and younger rocks, we know that's an unconformity. These are flat-lying sediments on top of an unconformity with these red and yellow colours below. Dikes you've probably encountered several times now, things cut straight across the topography, and of course the stratigraphy must be an intrusion. A dike in this particular case, and then again folds. Not everything that looks like that is a fold, because it may be topography, but you should be able to work that out by now. If the fold is following the topography, it's not a fold. So we take all this sort of information and we can use that to make cross sections in the same sort of way that you have been doing. So again, marking in the topography, then putting on the geology, and then using your protractor to measure the dips from the map, making a correction where necessary for any obliquity between the line of the section and the dip direction on the map. Relatively simple then to transfer the tilt on the geological units onto your cross section. And one important thing to do here is to remember not only to draw in the subsurface, but also to extrapolate into the air above the topography as well, so we can see what was missing. But I would definitely start with what's under the unconformity, well, the land surface. It's just a modern unconformity. So when you then begin to write your geological history, we can use the techniques that you've been practicing up to this point. You can use the geometries to note which ones come first and which cross-cut later. We'd also expect you to make some interpretation of the rock types, the lithologies, what you think those mean, what that means for the environment of deposition, for the type of deformation. And you can do that yourself from the geological map, but it is good when possible to supplement this with information from the geological literature where that exists, at least to some extent. And you can look for that in online databases. GeoRef is a pretty good one. Of course, a lot of people search these days on Google Scholar. It's quite easy to type something in and find links to papers, which are, at least on campus, you should be able to have access to. If you're working in the UK, the British Geological Survey also have a database and basic information about ages and different different styles of formations that we find in different parts of this country. And of course the same is true in many other countries overseas where there is a geological survey that's compiled extensive maps, which is in most places these days. So let's think about, finally, before we wrap up, mention something about drift. Drift is sort of like a slightly rude word in my opinion these days. What they really mean are superficial deposits, usually quaternary. That means they might be younger than 2.6 million years old. And what those usually mean, especially on British maps, is that they're either alluvium on the bottom of valleys, they might be beach sand or glacial till. These are glacial deposits here. They can be important, of course, depending on what you're interested in. If you're working with engineering geology, these may be very important and you maybe don't exclude them. But essentially, because they tend to be thin, they don't show up on cross sections, and so you could feel justified in not putting them on your geological map. Your simplified map might exclude the drift if that is obscure, if it's not being used in drawing the cross section. So it's something you should be aware of. Whether to include it or not, sort of up to you, and it depends what you're trying to achieve. So let's recap what I hope we learned here. So geological surfaces interact with topography to form the outcrop patterns, and that we can quantitatively describe geological surface using structure contours, and we learned how to draw cross sections from those. Now you're going to get into the nitty gritty of real geological maps. You're going to draw a series of sketch maps from 3 real British Geological Survey maps. I recommend that you spend about an hour on each one. First of all, we're going to try and simplify the stratigraphy in the way I showed, and trying to keep them into proportions. And then next week we're going to do something a little bit more serious. Instead of just simplifying the map, we're going to make a sketch map, a simplified map, but also then a cross section of vertical stratigraphy, and then work on trying to understand how you'd use those to generate a geological history. And that will be also essentially practicing the skills you need to do well in your final exam at the end of the academic year. Okay, thank you.